Hi, I'm John Paul Raj, and I'm on a mission to make the learning of math fun. So if you're new to this channel, please do consider subscribing. This is part 2 of quadratics, and on this video, we're going to talk about some of the key features of the quadratic curve. Let's start. In part 1, we saw that when we plotted these points, the coordinates where the x coordinates had the first differences as constant, whereas the corresponding y coordinates, the second differences were constant, not the first difference, but the second difference were constant. But if you pay close attention, each of the y coordinates is the square of the corresponding x coordinates. See, 4 is the square of 2, 9 is the square of 3, 16 is the square of 4, and 25 is the square of 5. And so each of those coordinates were of this form where you had the y coordinates with the square of its corresponding x coordinate. And when we plot all such points, we saw it on the first video. If you've not seen that video, I'm going to link that video in the description box below. Please go ahead and take a look at that. When we plot all these points of the form where the y coordinate is the square of the corresponding x coordinate, we get a parabola. And so this is a parabola whose equation we say is y is equal to x squared. Y is equal to x squared, okay? Because every y value is the square of the corresponding x value. The general form of a quadratic equation is ax squared plus bx plus c. Now, when you're in standard 8, 9, and whenever you do quadratic equations at the earlier stages in school, we normally don't see the curve and we don't even see the y value there. So you might be wondering what's going on. Well, actually, this is the y value for a corresponding x value. So it literally means for some value x, the corresponding y value is ax squared plus bx plus c, which means that this y is equal to x squared is the original parent graph. Okay, I don't want to use the word function to confuse those of you who are in grade 9 or 10. Okay, so I'm just going to call it the original graph. Whereas when you have ax squared plus bx plus c, it's just some kind of a modification from that original graph, okay? So when you multiply by a times x squared, it'll change slightly. When you add a bx to that ax squared, it'll change even more slightly. And when there's a c element also added to that expression, the graph will change. So this is the original graph, and ax squared plus bx plus c is some kind of a modification from the original graph. Now let's make some observations about this parabola or the quadratic curve. The first thing is that when a is positive, we'll get this U-shaped parabola, or the quadratic curve is U-shaped. Whereas when a is negative, we'll get this inverted U-shaped parabola. The quadratic curve becomes inverted U. That's the first observation. The coefficient of x squared, whenever a is positive, you'll get a U-shaped parabola. Whenever a is negative, you'll get an inverted U-shaped parabola. And to get some idea of what this a, b, and c do to the original quadratic curve, let's just jump to our graphing calculator and see. I've got this original quadratic curve here in red, and I've just created these sliders for a, b, and c. As you can see, first value, the original value of c is 0 and b 0, a is 1, and that gives us the original parent quadratic curve, all right, the parabola. When I change the value of a, notice how the quadratic changes now, okay? Just these might be subtle changes because it's just increasing by 0.1. Can you see how the red graph has changed? The blue is the original one, okay? So if I'm going to change a again, by 0.1, can you see? It's more or less moving closer to the y-axis, but that a, and when I decrease the value of a, notice the change, okay? It's becoming wider now, okay? So that a, all I'm trying to illustrate is that there are subtle changes that a, b, and c do to the original graph. The original graph is the blue graph. And as I kept making changes for a, you could see how the red graph has changed from the original, all right? So in the same way, if I just add on some values for b other than 0, look at the graph, okay? It's just moving to the left-hand side, and oh, now there's cutting the x-axis somewhere. Can you see that? So as you can see, now there is a value for a, there's a value of b, and that original graph has moved away. In the same way, when you move c, okay, if you add c value, can you see that it's going up? All right? And when we decrease the values of c, it's going down. This was just to illustrate how that a, b, and c affect the movement of the original quadratic curve, how by changing the values of a, b, and c, the original quadratic curve moves along the coordinate plane. Because otherwise, when we just look at a, b, and c as a coefficient of x squared, the coefficient of x, and the constant term, we are just limited to the algebra. But it will also be helpful in understanding quadratics better when we see how a, b, and c have shifted or moved or even expanded the original quadratic curve. The second feature that I want to highlight is this point where the quadratic turns around. The turning point, that's also referred to as the vertex. Okay, so the vertex when a is negative also is the point which we will call the minimum value of the quadratic. It's the lowest value that the quadratic will take, okay? The vertex is the point where we'll have the minimum value when a is positive, and when a is negative, that's the vertex, the turning point, okay? That's the vertex. And that will be the maximum value for the quadratic, okay? When a is negative, the vertex is where the quadratic attains the maximum value, whereas when a is positive, the vertex is where the quadratic will attain the minimum value. The third feature of the quadratic graph that I want to highlight is this line of symmetry. The quadratic is symmetric, and this is a very powerful property, okay, that it is symmetric. In this case, the original graph is symmetric about the y-axis, the line of symmetry, if you were to call it. Can I write it somewhere here? Line of symmetry, LOS stands for line of symmetry, is the y-axis. The equation of the y-axis is x is equal to 0. So the parent or the original quadratic curve is symmetric about the y-axis, and that, like I said, is going to be a very powerful thing. And you can see that the line of symmetry goes through the vertex, okay? It passes through the vertex. Likewise here also, when a is negative, it's its same axis of symmetry or line of symmetry as we call it, okay? And that again passes through the vertex. So here again, the line of symmetry, let me just write it as LOS, is y-axis. X is equal to 0 is the equation of the y-axis, okay? So there are three things that we've seen. One is that a is positive gives you a U-shaped parabola, whereas a is negative gives you an inverted U-shaped parabola. We talked about the vertex. That's where when a is positive, you've got the minimum value. At the vertex, when a is negative, you've got the maximum value. And the third thing we saw was the symmetry, the y-axis being the axis of symmetry, and how that passes through the vertex, the line of symmetry going through the vertex. Now, the vertex is also the point where this original parabola, the original quadratic curve, cuts both the x-axis and the y-axis. Those points are called intercepts, by the way. X-intercept is where the graph cuts the x-axis, and y-intercept is the point where the graph cuts the y-axis, all right? So the x-intercept and the y-intercept for the original quadratic curve is still the vertex, okay? Now, all of this, the vertex, the line of symmetry, the x-intercept, the y-intercept, all of that will change when you have ax squared plus bx plus c, because as we saw in the calculator, that the moment you have ax squared plus b plus c, different values for a and c, can you see that the graph is shifting, which means the line of symmetry will change. You've got new x-intercepts, you've got another y-intercept. So the whole point of quadratic equations is then to find all these key features of the graph. All the algebra that we do, okay, when we are trying to solve the quadratic equation, when you're factoring, when you're using the quadratic formula, all the algebra that we do is related to this graph and related to the key features of the graph, namely finding the vertex, finding the line of symmetry, finding the intercepts, the x-intercept and the y-intercept. I'm going to draw a general quadratic. So let's draw the axis first. Okay, that's going to be our coordinate axis. That's the x-axis, the y-axis. Can you guys see this? All right, there we go. Here we go. Okay, now I'm going to draw the quadratic curve, a general quadratic, okay, just like that. That's my quadratic. I'm going to call this ax squared plus bx plus a c, okay? And that means this is going to be my vertex, and we have already seen that the line of symmetry should pass through the vertex, okay? Line of symmetry. That's my vertex. Let me just quickly write it down there. That's my vertex. And here, remember that we are assuming that a is positive, okay? That a is positive, and therefore we have a U-shaped parabola. That's the line of symmetry going through the vertex. And what else can I mark? I can mark this point as my x-intercept. My y-intercept is here. This is just something general I've made up, okay? If you have a general quadratic expression, something like that, that's c, the constant term c gives us the y-intercept. So the coordinates of the y-intercept are basically 0, c. Just from that expression, ax squared plus bx plus c, you can tell that that c is going to give us the y-intercept. Even if it were an inverted U-shaped parabola, okay, inverted U, that c, the moment you have a c, that's going to give you the coordinates of the y-intercept. The x-intercept, these are key, all right? X-intercept is when y is equal to 0, okay? So literally the y value is 0, and these are your roots. or what you sometimes call the solution. Okay, these two. So I'm going to call this x1 and x2. x1 and x2 are the roots of the solution. All the methods that you have, the method of factoring, the method, the quadratic formula, all those that you use are actually to find the roots or the x-intercepts. The line of symmetry is x is equal to negative b over 2a. So the moment you see a quadratic given in its general form, there are many things, there are many features of the graph that you can just manipulate even without using any graphing calculator. Okay, the first thing being that when a is positive, what kind of curve is it going to be? Is it going to be u or is it going to be inverted u? You can tell that by just looking at the quadratic expression. You can even tell what the y-intercept is going to be. 0 comma c is going to give you the y-intercept. You can even tell the equation of the line of symmetry. X is equal to negative b over 2a. And because we have already noted that the vertex goes through that line of symmetry, the x-coordinate of the vertex is going to be negative b over 2a. So the x-coordinate of the vertex is going to be negative b over 2a. The y-coordinate, I'll put a question mark. We'll come back to that later. And before we wrap up, let's quickly check our understanding of what we have seen in this video, right? The first one is the parent quadratic. We won't talk about it, but let's look at these ones. These are the general form, okay? So first thing to know, what can we tell from a quadratic just given like this, okay, without a graphing calculator? Well, A is positive, so this should be a U-shaped parabola. C, we know something about C, okay? So that means the y-intercept is 0, 3, okay? The line of symmetry, the equation of the line of symmetry, I'm going to write LOS again, is going to be x is equal to a negative b over 2a. The b is 6, so it's a negative 6 over 2 times 4, which is going to be negative 3 over 4. Yeah, so x is equal to negative 3 over 4 is going to be the equation. You can see this equation of the line of symmetry for the first graph. So three important features of the graph of a quadratic when it is just given in its algebraic form can be just stated just like that. Okay, let's look at the next one. Okay, so we have y is equal to negative x squared minus 4. This is going to be an inverted U-shaped parabola because a is negative, all right? And then that's our c. So we can say that the y-intercept is going to be 0, a negative 4. Remember, c is negative 4. What else can we say? We can say that the equation of the line of symmetry, LOS, line of symmetry, is x is equal to negative b over 2a. Well, there is no b term. That means it's just going to be equal to 0 over 2a, which happens to be 0. So line of symmetry, equation of the line of symmetry is x is equal to 0, which is again the y-axis. And for the third example, again, we have the value of a is negative. That means here again, it's going to be an inverted U-shaped parabola. We don't have a c term, okay, which means that the y-intercept is going to be 0, 0. And the line of symmetry, the equation of the line of symmetry is negative b over 2a. That's x is equal to a negative 6 over 2 times a negative 10, which works out to 3 over 10. Is that right? So x is equal to 3 over 10 is going to be equal to the equation of the line of symmetry. We will continue with our discussion on quadratic equations in the next video. See you then.